Hello and welcome to this video about matrix proofs. In this video we'll prove 4 matrix inverse lemmas. We'll start off with this lemma that if there are 2 inverses of a matrix being left and right inverses, denoted by L and R, then they must be equal. If a matrix is an inverse, then it is both a left and right inverse. So now to start this proof, we'll start with the left inverse and try to get the right. We can multiply it by the identity, which is its main property. In a proof we can do it in reverse because we're trying to prove a result and not solve an equation. Then we can expand the identity into this being a product of a matrix and its inverse. Then we can use associativity to move the brackets. We can simplify this to be the identity because L is the left inverse of A. And we can simplify this equation by eliminating the identity. So that's it. We've proven that the left and right inverses of a matrix must be equal. So now to prove that every elementary row matrix has an inverse, that is, every row operation matrix has an inverse. We've done this before in a past theorem, when I had to show that row equivalency is an equivalence relation, and it was important to show it when proving symmetry. So I'll just do a word proof for now and refer you back to the past proof. So now to start this proof, we'll prove that each of the 3 sorts of row operation matrices has an inverse. It suffices to show it true for the actual operation, so as to show it to be true for the row operation matrix. We'll start with the row swap operation. Every row swap operation has an inverse, and it is its own inverse, because it will swap the 2 rows back to where they started if it's done twice. I guess that's pretty obvious. So every row mul operation has an inverse. If a row mul operation multiplies a particular row by a constant C, then multiplying this row by the reciprocal of C will get it back to its original condition, so it will be its inverse. This constant C must be non-zero. And every row add operation has an inverse. If this row operation adds C times a row I to another row J, then its inverse is to add minus C times row I to row J to get this matrix back to its original condition. This operation leaves row I untouched, so that it can be subtracted from row J to get the row J that we started with. So that's all 3 types of row operations shown to have inverses, so that proves this lemma to be true. Now to prove this lemma, which is this equation that's hard to express in words. I'd like to show you this equation first, shown in colours that highlight the expressions that can be manipulated as though they were single variables. The product of these 2 matrices are manipulated together as though they were single variables, to show that this expression AB in brackets raised to the power of minus 1 is the inverse of AB. To prove it true, we'll have to show that this is both a right and left inverse, because inverses can't easily be manipulated into long strings of equalities, like in the first lemma in this video. We'll start with the top equality to show that it's a left inverse. We can swap the brackets using associativity. We can be a bit lax with it and manipulate these brackets using 4 variables. So these matrices A and A inverse multiply together to give the identity. And then this identity can be eliminated because it functions like the number 1, to be eliminated in algebra when used in multiplication. Then these 2 matrices form a matrix inverse pair and thus multiply by each other to become the identity. So we've proven it to be a left inverse. Now to prove it to be a right inverse as well. So if we multiply this matrix on the right, we can swap the brackets using associativity. Then this inverse matrix pair multiply together to become the identity. And the identity can be eliminated. It can be absorbed by any variable on either side. Then this matrix inverse pair can be multiplied together to give the identity, thus proving the result. I hope that you can see how the positioning of these inverse matrices acts to make it into an inverse of this product. So now to prove this obvious equation, that the inverse of the inverse of A is A. I'd just like to show you this picture first, that this expression behaves like the inverse of A, so that you can get the idea of what to look out for. I put them in brackets so that these complex expressions can be manipulated as though they were single variables. We can use the definition of matrix inverses to write this equation. We can see how the inverse of matrix A can multiply on either side to give the identity, which functions like the number 1. But if you look carefully, the matrix A multiplies on both the left and right of the inverse of A, and behaves like the inverse of matrix A because of this. So A is both a left and right inverse of A to the power of -1, so it's an inverse of this matrix, and satisfies the conditions to be the inverse of A. So A is the inverse of A. And so we can write this equation mathematically, where the inverse of A is equal to A. So now we've proven the fourth lemma. So I hope that you've found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.